Welcome to the Deep Dive. You know, we love to go deep on all sorts of topics, and today we're diving into the world of systems performance.
Oh, yeah, this will be fun.
We've got some excerpts from the book Systems, Performance, Enterprise, and the Cloud.
It's a good one.
And we're going to unpack some of the key ideas for making computers run at their best.
Absolutely.
Whether it's your own laptop or a massive cloud server, everyone wants things to run smoothly.
Right, and there's so much to think about when it comes to performance. It's not always obvious what's causing a bottleneck.
And that's what's so fascinating about it. It's like a detective story.
Yeah, I like that analogy.
You start with a symptom, like a slow application.
Right, or maybe a website that's taking forever to load.
And then you have to track down the root cause, which could be anywhere in this complex web of hardware and software.
It's like a puzzle sometimes. You have to put all the pieces together to see the bigger picture.
The book actually opens with this great anecdote about senior system administrators who were almost like magicians.
Oh, yeah, I remember that.
They could diagnose performance issues with just a few commands and their years of experience.
It's amazing what some of those folks can do, just incredible intuition.
The author contrasts that with like the dryness of technical manuals and says, there's a methodology missing from manuals.
Yeah, you can read all the specs and documentation in the world, but it's that real-world experience that often makes the difference.
It's not just about knowing the technical details, right?
Right. It's about having a framework, a way of thinking about performance that guides your investigation.
And that's where the USE method comes in, I think.
Yeah, the USE method. It's like a universal translator for performance analysis.
Can you tell us more about that? I've heard of it, but I'm not really sure how it works.
So it stands for utilization, saturation, and errors.
Okay, so 3 key things to watch out for.
Exactly. And the beauty of it is its simplicity and broad applicability.
So we can use it for just about anything.
Yeah, you can apply it to any system resource from your CPU and memory to your network interface and even software-defined resources in the cloud.
Oh, wow. So it's not just for physical hardware.
Nope, it works for virtualized environments too, like cloud computing and containers.
That's pretty cool. So it's a way to get a quick health check on any component to see if it's struggling.
That's a good way to put it, a health check for your system.
I like that.
Mm-hmm.
So can you break down those 3 terms a little more for us? What exactly are we looking for when we're talking about utilization, saturation, and errors?
Sure. So utilization is all about how much work a resource is doing at any given time.
Okay, so how busy it is, essentially.
Yeah, but it can be a little more nuanced than that.
Oh, how so?
Well, for something like memory, it's about how much of the capacity is being used, like how full is your RAM.
Right, that makes sense.
But for a CPU, it's more about the percentage of time it spends actively processing instructions.
So it's not just about how much data is stored in the CPU, but how much work it's actively doing.
Exactly.
Okay, so a CPU running at 80% utilization means it's spending 80% of its time doing actual work.
Yeah, that's right.
Makes sense. What about saturation? How does that come into play?
So saturation happens when a resource has more work than it can handle and requests start piling up waiting their turn.
Oh, so it's like a traffic jam.
Yeah, that's a good analogy.
Everything gets backed up, even though there's plenty of capacity.
Exactly. Think of it like a busy restaurant kitchen during the dinner rush.
Oh, I can picture it.
Even if the cooks are working nonstop, there are too many orders coming in, you'll have a backlog.
Right, and the food will start to get cold and the customers will get impatient.
Exactly. And in a computer system, this backlog can manifest as delays and slowdowns.
So it's not just about how busy a resource is on average, but also about those peak moments of demand, right?
Precisely. Those bursts of activity can really lead to bottlenecks.
Even if things are calm most of the time.
Yeah, those brief periods of saturation can have a big impact on overall performance.
Interesting. So we've got utilization, saturation, and the third one was errors, right?
Errors.
I guess that one's pretty self-explanatory.
It might seem straightforward, but it's worth emphasizing that even errors that don't crash your system, those so-called recoverable errors, can still degrade performance.
Oh, so even if things seem to be working, those errors could be a sign of underlying issues.
Exactly. They're like little warning signs that something isn't quite right and needs further investigation.
So it's important to pay attention to those errors, even if they don't seem to be causing any immediate problems.
Absolutely. They can be a valuable clue in our performance detective work.
Okay, so the USE method gives us a framework for identifying potential performance issues across all sorts of system components, both physical and virtual.
Yeah, it's a powerful tool for getting a quick overview of your system's health.
But let's say we've used the USE method and we've identified some potential bottlenecks. What's the next step? How do we actually go about investigating those issues and finding the root cause?
That's where the concept of observability and experimentation comes in.
Ah, so we need to go beyond just looking at the numbers.
Exactly. You can't solve a performance mystery with just one of these. You need both observation and experimentation.
The book actually quotes a senior performance engineer who says, you have two hands, observability and experimentation.
I love that quote. It really drives home the point that you need both approaches.
So observational tools provide a window into how your system is behaving in real time, right?
Right. They give you valuable insights into what's actually happening under the hood.
So things like system logs, performance counters, and monitoring dashboards. Those would be examples of observational tools, right?
Exactly. They let you passively observe the system without directly interfering with its operation.
But to really get the full picture, you also need to actively experiment with the system.
That's right. Observation is just one side of the coin. You need to poke and prod a bit to see how the system reacts.
So what does experimentation look like in the context of performance analysis?
It can involve things like running benchmarks to test specific components under controlled conditions.
So you're creating artificial workloads to see how the system handles them.
Exactly. It allows you to isolate variables and understand cause and effect relationships.
And you can also intentionally introduce load to see how the system responds, right?
Right, like simulating a sudden surge in traffic to a web server.
That's where things like load testing and micro benchmarks come into play.
Exactly. And by combining those experimental insights with your observational data, you can start to build a comprehensive understanding of your system's performance characteristics.
So you move from what is happening to why it's happening.
Precisely. You become a performance detective.
I like that. So we've got our USE method for initial assessment, and then we use observation and experimentation to dig deeper.
It's a powerful combination.
But before we get into specific tools and techniques, I think it's worth talking about a fundamental concept that often comes up in performance discussions: scalability.
Ah, yes, scalability. A crucial concept, especially as systems grow and demands increase.
It's all about how a system handles increasing load,
Right.
right? Whether it's more users, more data, or more transactions.
Exactly. Does it gracefully handle that growth, or does it crumble under pressure?
And the book describes this typical throughput profile, where for a while, as you add more resources, you get a proportional increase in performance. Things scale nicely.
Yeah, it's that beautiful linear scalability.
But then you hit a point where adding more resources doesn't give you the same bang for your buck.
Right, you hit that dreaded knee point.
What's happening there? Why does that happen?
It's usually because contention for a shared resource starts to become a major bottleneck.
So even if you have plenty of CPU cores or memory available, if everyone is trying to access the same disk or database, you're going to run into problems.
Exactly. It's like having a 10-lane highway that suddenly narrows down to a single-lane bridge.
Ah, I see. No matter how many cars you have on the road, they're all going to get stuck at that bottleneck.
Precisely. And that's where understanding Amdahl's law becomes crucial.
Amdahl's law, what's that all about?
It's a mathematical principle that helps us understand the limits of scalability.
Oh, okay, so it tells us how much we can realistically expect to improve performance by adding more resources.
Exactly. It basically states that the maximum speedup you can achieve by parallelizing a task is limited by the portion of the task that cannot be parallelized.
Okay, that sounds a bit technical. Can you give us a real-world example to make it clear?
Absolutely. Imagine you're baking a cake.
I love baking cakes.
Some parts of the process can be done in parallel, like mixing the dry ingredients and the wet ingredients separately.
Right, I always do those separately.
But there are certain steps that have to be done sequentially, like adding the wet ingredients to the dry ingredients and then baking the cake.
Yes. You can't really bake the cake until you've mixed all the ingredients together.
Exactly. No matter how many helpers you have in the kitchen, those sequential steps will always limit how quickly you can bake the cake.
So even if I have a team of expert bakers, we're still going to be limited by the inherent sequential nature of certain tasks.
Precisely. And Amdahl's law helps us quantify that limitation. It tells us that if, for example, only 50% of a program can be parallelized, you'll never achieve more than a 2x speedup, even with an infinite number of processors.
So there's always going to be some part of the task that can't be sped up, no matter how much horsepower we throw at it.
Exactly. It's a fundamental limit that we have to be aware of.
That's a really helpful way to think about it.
Yeah.
So when we're designing systems for scalability, we need to carefully consider both the parallel and sequential aspects of the workload.
Absolutely. and find ways to minimize those sequential bottlenecks.
And there are various strategies we can employ, right? Like breaking down large tasks into smaller, more parallelizable chunks.
Exactly. Or using caching to reduce the need to access shared resources.
Caching. And speaking of which, that's a topic I'm always eager to learn more about. It seems like magic sometimes. Can you give us a primer on caching and how it helps boost performance?
Sure. So caching is all about bringing frequently used data closer to where it's needed so you don't have to waste time fetching it from slower storage locations.
So instead of fetching data from main memory or disk, which can be slow, you store it in a faster, more readily accessible cache.
Precisely. It's like having a mini library in your office instead of having to go to the main library every time you need a book.
I love that analogy. It makes so much sense.
And there are multiple levels of caching, each with its own speed and capacity trade-offs.
Like those L1, L2, and L3 caches we hear about in CPUs. What are those all about?
Those are incredibly fast caches built right into the CPU itself. L1 is the fastest and smallest, holding only the most recently used data.
So it's like having a sticky note on your desk for the most important information.
Exactly. Then you have L2, which is a bit slower and larger.
Like a small notepad on your desk.
Right. And then L3 is even larger and slower, but still much faster than accessing main memory.
So it's like having a filing cabinet in your office.
Exactly. It's a hierarchy of mini libraries, each level getting bigger and slower, but still much faster than going to the main library.
And beyond CPU caches, you have things like file system caches, which store frequently accessed files in RAM.
Right. And even second-level caches that use flash memory to store data that's not quite as hot, but still accessed more frequently than data on disk.
So there are all these different levels of caching working together to keep things running smoothly.
It's amazing how much complexity is hidden beneath the surface.
It really is. And managing those caches effectively is crucial for optimizing performance.
Absolutely. But sometimes you need to dig deeper than just caching. Sometimes you need to understand how your applications are actually using those system resources.
And that's where profiling and tracing come into play, right?
Precisely. Profiling helps you understand which parts of your code are consuming the most resources, while tracing allows you to follow the execution flow of your program and see exactly what's happening at each step.
So profiling is like taking a snapshot of your code's resource usage, while tracing is like recording a video of its execution.
Great analogy. And with the right profiling and tracing tools, you can pinpoint bottlenecks in your code, identify areas for optimization, and get a much deeper understanding of how your applications are interacting with the underlying system.
That sounds incredibly powerful. But before we dive into that world, let's take a quick detour and talk about another important technique, micro-benchmarking.
Oh yes, micro-benchmarking. A valuable technique for isolating and testing the performance of very specific components or code paths.
So it's about creating small artificial workloads that stress a particular aspect of the system and allow you to measure its performance in isolation.
Exactly. It's like running a series of controlled experiments in a lab.
To see how each piece of the puzzle performs under stress.
Precisely. And it's especially useful for comparing different implementations of the same functionality or for understanding how performance changes as you tweak specific parameters.
So you can really fine-tune things at a very granular level.
Right. And the book mentions a tool called FIO that's commonly used for micro-benchmarking disk I/O performance.
So you can use it to simulate different workloads like random reads and writes, sequential reads and writes, and even mixed workloads.
Exactly. This allows you to understand how your storage system performs under different types of pressure.
That sounds incredibly useful for anyone working with data-intensive applications.
It is. But before we get too carried away with tools and techniques, let's take a step back and talk about another key factor that can impact performance virtualization.
Ah, yes, virtualization. It's become so ubiquitous these days, especially with the rise of cloud computing and containers.
It's a powerful technology that allows you to run multiple operating systems and applications on a single physical server.
Which is great for resource utilization and flexibility.
Absolutely. But it also introduces an extra layer of complexity that needs to be considered when analyzing performance.
Because now you have this shared environment where multiple virtual machines or containers are competing for the same physical resources.
Exactly. And those resource controls we talked about earlier can create contention and bottlenecks, even if the physical server has plenty of capacity available.
So it's like having a large apartment building with multiple tenants sharing the same utilities.
That's a great analogy. Even if the building has plenty of water and electricity, if everyone tries to use the shower and washing machine at the same time, you're going to run into problems.
Right. It's all about managing those shared resources effectively.
And that's where understanding how virtualization works and how to monitor and manage resource usage in a virtualized environment becomes crucial.
So we need to be aware of those potential bottlenecks and have the right tools to diagnose them.
Exactly. And thankfully, those tools are evolving to become more container aware,
Hmm.
allowing you to filter events and see only those that are relevant to a specific container.
That's like having a special set of glasses that lets you see only the traffic patterns within a specific neighborhood, even though there are cars driving all over the city.
Perfect analogy. It's all about focusing on the right details.
Well, this has been a really fascinating overview of some of the key concepts in systems performance.
It's a complex but fascinating field.
And we've only just scratched the surface.
There's so much more to explore.
But before we get lost in all the details, why don't we take a break and come back with part 2, where we'll dive into a specific case study and see how all these concepts come together in a real-world scenario.
Sounds good to me. I'm looking forward to it.
Stay tuned for part 2 of the deep dive.
So, we were talking about how performance analysis is like detective work.
Yeah, it's all about finding those clues and piecing together the puzzle.
Right. Well, I've got a case study that I think really illustrates that point.
Oh, perfect. Let's hear it.
All right, so this story starts with a system administrator named Sumit who's facing a pretty common problem. Database queries are running super slow.
Oof, I know that feeling. It's like watching paint dry.
Exactly.
Yeah.
And Sumit's first instinct, like many of us, is to suspect the disks.
Makes sense.
Right.
They're often the culprit when things are slow.
Right. So he starts by using a tool called IOStat.
IOStat, that rings a bell. What did
Yeah.
that do again?
It basically gives you a snapshot of disk activity. You know how busy they are, what kind of operations they're performing, things like that.
So it's providing the raw data, but how does Sumit make sense of it all?
That's where experience and a good methodology come in handy. He notices that the disk utilization is quite high.
Which could certainly point to a bottleneck.
Right. But instead of jumping to conclusions, he digs a little deeper.
Smart man.
He uses some additional options with IOStat to gather more granular data.
Like what kind of data?
Things like IOPS throughput and average latency.
Okay, getting into the nitty-gritty.
Yeah. He's not just looking at the big picture, he's looking for patterns in the details.
So it's not enough to just see high numbers. You need to understand what those numbers mean in the context of the overall system.
Exactly. And in the context of the specific workload.
Right, because what's considered high for one application might be perfectly normal for another.
And this is where Sumit's methodical approach, guided by the USC method, really pays off.
The USC method strikes again.
He realizes that while the disks are busy, they're not actually showing any signs of distress or malfunction.
So that I'm failing or anything like that.
Nope. They're simply being asked to do a lot of work.
So the disks themselves aren't the bottlenecks. They're just the victims of a demanding workload.
Exactly. They're just trying to keep up.
Okay, so now the mystery deepens. If it's not the disks, then what's causing that surge in demand?
That's the million-dollar question, right?
Where does Sumit go from here?
Well, he shifts his focus from the hardware to the software and user behavior.
So he's moving up the stack, looking beyond the immediate symptoms.
Precisely. He's thinking bigger picture now.
I like it.
He asks himself, has the database load increased recently?
Good question. Has there been a change in user behavior? Maybe a new application that's putting a strain on the system?
Exactly. All possibilities. That wouldn't be apparent if he just focused on the disks themselves.
So it's all about connecting the dots and seeing the bigger picture.
Right. And this is a perfect example of how the USC method, combined with a methodical approach, can save you a lot of time and effort.
It's like eliminating suspects in a detective case.
Exactly. You rule out the obvious culprits and then you start digging deeper.
And sometimes the answer is hiding in plain sight.
It can be, but you need that broader perspective to see it.
This case study also reminds us that understanding your workload is critical.
Absolutely. You can have the best hardware in the world, but if your software or users are making inefficient requests, you're going to run into performance issues.
It's like having a Ferrari stuck in rush hour traffic.
The potential for speed is there, but it's being hampered by external factors.
So we've talked about the USE method as a general framework for performance analysis.
A good starting point.
And we've seen how a methodical approach combined with a deep understanding of the workload is crucial for effective troubleshooting.
But now let's talk tools.
Yes, the tools of the trade. I'm ready to get my hands dirty.
All right, so the book mentions a whole arsenal of tools for monitoring, analyzing, and optimizing performance.
Where do we even begin? There are so many.
It can definitely feel overwhelming. But remember, the performance engineer's advice, we have two hands, observation and experimentation.
Two hands, two approaches.
Let's start with some key observational tools that give you a window into your system's behavior.
Okay, sounds good. What have we got?
One of the most versatile and powerful tools for system monitoring is SAR, which stands for System Activity Reporter.
SAR. Okay, I've heard of that one. What's
Yeah.
so special about it?
It's like a time machine for performance data. It allows you to collect and analyze historical data about various system metrics.
So you can see how things have changed over time.
Exactly. You can track things like CPU utilization, memory usage, disk I/O activity network traffic, and much more.
So you can use it to answer questions like, did CPU utilization spike after we deployed that new code?
Yeah,
Or is disk I/O activity consistently higher during certain hours of the day?
exactly. It's a fantastic tool for historical analysis and troubleshooting.
Very cool. But what about real-time insights? What if I want to see what's happening right now?
Well, for that, there's the classic top command.
So top, good old top.
It shows you a dynamic, real-time view of the processes that are consuming the most resources.
So it's like a live dashboard for your system.
Exactly. You can see which processes are hogging the CPU or memory.
Very helpful for identifying potential troublemakers.
But sometimes you need to go beyond the system-level view and look at specific processes in more detail.
So if I see a process in top that's using a lot of CPU, how can I dig deeper and understand what's going on within that process?
For that, we have PIDStat,
PIDStat.
another one to add to the toolbox.
It's basically top, but for individual processes. It gives you a detailed breakdown of resource usage for a specific process.
So if we suspect a process is causing performance problems, we can use PIDStat to get a closer look.
Exactly. And by comparing the PIDStat output for different processes, you can start to understand how they're interacting with each other.
And how they're interacting with the underlying system.
Right, it's all about getting that holistic view.
So SARTOP and PIDStat, those are our three musketeers of observation.
They're a good starting point. But there's a whole ecosystem of tools out there, each with its own strengths and weaknesses.
It's like having a different tool for every job. Exactly, and it's important to choose the right tool for the task at hand.
Okay, so we've covered observation. But what about experimentation? What are some common experimental techniques in performance analysis?
Well, one of the most powerful techniques is benchmarking.
Benchmarking, I've heard that term thrown around a lot.
Yeah.
What exactly does it mean?
It involves running a set of standardized tests or workloads against your system to measure its performance under controlled conditions.
So you're essentially putting your system through its paces to see how it handles different types of load.
Exactly. And there are different types of benchmarks, each with its own purpose.
Like, what are some examples?
You might have benchmarks that are designed to stress the CPU, the memory, the disk I/O, or the network. You might also have benchmarks that are designed to simulate real-world workloads like web server traffic or database transactions.
So by choosing the right benchmarks, you can get a pretty good understanding of how your system will perform under various conditions.
Exactly. And benchmarking is not just about measuring raw performance. It's also about understanding how performance changes as you tweak different parameters or configurations.
So you can use benchmarks to test the impact of things like different hardware configurations, software optimizations, or even just changing the values of certain system parameters.
Precisely. It's a very powerful technique for understanding cause and effect in performance analysis.
Very cool. And it's often used in conjunction with micro-benchmarking, right?
Yes, they complement each other nicely.
Right. Micro-benchmarking is about isolating and testing very specific components or code paths, whereas benchmarking is more about testing the system as a whole.
Exactly. Different levels of granularity.
This is all fascinating stuff.
Yeah.
But before we get too carried away with all the tools and techniques, let's talk about another crucial aspect of performance analysis that's often overlooked: profiling.
Ah, yes, profiling. It's like shining a spotlight on the inner workings of your code.
What exactly is profiling and why is it so important?
It helps you understand which parts of your code are consuming the most resources, like which functions are the real hogs.
So it's like having a detailed accounting of your code's resource usage.
That's a great way to put it. It shows you where all the energy is going.
And the beauty of profiling is that it can be done at different levels of granularity, right?
Exactly. You can profile the entire system, a specific process, or even individual functions.
So depending on the level of detail I need, I can choose the right profiling tool and approach.
Precisely. And there are different types of profiling as well. CPU profiling, for example, tells you which functions are consuming the most CPU time.
So if my application is running slow, CPU profiling can help me pinpoint the functions that are slowing things down.
Exactly. It's like finding the bottleneck in a factory production line.
What are some other types of profiling?
Well, there's also memory profiling, which helps you identify memory leaks.
Memory leaks. Those sound bad.
They can be.
Yeah.
They're essentially when your program keeps allocating memory but doesn't release it when it's no longer needed.
So it's like hoarding old newspaper.
Kind of. It can eventually lead to your application consuming way more memory than it needs.
And that can slow things down to a crawl.
Exactly. And memory profiling tools can help you track down those leaks so you can fix them.
That's good to know. Are there any other types of profiling that are worth mentioning?
There's also I/O profiling, which can help you understand how your code is interacting with the disk or the network.
So if you're doing a lot of file reading or writing or network communication, I/O profiling can help you identify bottlenecks in those areas.
Exactly. It's all about understanding how your code is using system resources.
This is all starting to make sense now.
Okay.
So with all these different types of profiling, we can really get a comprehensive understanding of what's going on under the hood.
Exactly. It's like having X-ray vision into your code.
But how do we actually make sense of all that data? It must be a lot to process.
Well, that's where visualizations come in handy.
Visualizations, like graphs and charts.
Exactly. Visualizing profiling data can make it much easier to spot patterns and identify areas for optimization.
So instead of staring at a wall of numbers, I can see the data in a more intuitive way.
Right. Have you ever heard of flame graphs?
Flame graphs. They sound a bit intimidating.
They're not too bad once you get the hang of them.
Okay, so what are they?
They're a way of visualizing profiling data that shows you the call stack of your program with the width of each bar representing how much time was spent in that function.
So the wider the bar, the more time it consumed.
Exactly. It's like a visual representation of your program's activity showing you the hotspots.
And you can click on a bar to zoom in and see more detail, right?
Right. It's interactive. You can really drill down and pinpoint those bottlenecks.
So it's like having a magnifying glass for your code.
Exactly.
Yeah.
And the best part is that they're relatively easy to generate. There are a number of tools that can create flame graphs for you.
This is all great stuff. But I think it's important to remember that the biggest performance wins often come from eliminating unnecessary work, not just from making existing work faster.
Absolutely. That's a
Yeah.
key principle of performance optimization.
So it's not always about tweaking algorithms or fine-tuning parameters. Sometimes the best solution is to simply remove code that's not doing anything useful.
Exactly. It's like decluttering your house. You get rid of the things you don't need, and suddenly everything feels more spacious and efficient.
And less cluttered code is easier to understand and maintain, which is a win for everyone.
Absolutely. But of course, there are times when you do need to delve into those nitty-gritty details.
And that's where all those tools and techniques we've been discussing come into play.
Right. It's all about finding the right balance between eliminating unnecessary work and optimizing the work that's essential.
And it's an iterative process, right? You make a change, monitor the impact, and adjust accordingly.
Exactly. It's like a dance between observation, experimentation, and optimization.
So with all these insights and techniques in our toolkit, what are some key takeaways for our listeners?
I think one of the most important things to remember is that performance optimization is not a one-time event. It's an ongoing process.
Because technology is always changing and workloads are always evolving.
Exactly. And it's important to have a solid understanding of the fundamentals like the USE method and the principles of caching parallelization and I/O optimization.
But it's also about being willing to experiment and learn from your mistakes.
Absolutely. And to embrace the fact that performance optimization is a journey, not a destination.
Well said. So with that in mind, let's move on to part 3, where we'll explore some specific optimization strategies and real-world examples.
Sounds good to me. Let's dive deeper. So we've talked about all sorts of tools and techniques for analyzing performance.
Yeah, we've really gone deep on observation, experimentation, profiling, you name it.
Right. But now it's time to put all that knowledge to good use.
Time to make those systems sing.
Exactly. Optimization time.
I'm excited.
Yeah.
What are some of the key strategies for making our systems run faster, smoother, more efficiently?
Well, remember that key principle we talked about earlier?
Remind me.
The biggest performance wins often come from eliminating unnecessary work, not just from making existing work faster.
Ah, yes. The decluttering principle.
Exactly. It's all about finding those areas where your system is spinning its wheels for no good reason and cutting them out entirely.
So before we even start thinking about fancy algorithms or optimizations, we should take a step back and ask ourselves, is there a simpler way to achieve the same outcome?
Exactly. Sometimes the most elegant solution is the one that does the least.
Less is more.
Precisely. But of course, there are times when you simply can't avoid doing the work.
Right. Some tasks are just inherently complex.
And in those cases, you need to focus on making that work as efficient as possible.
And that's where all those tools and techniques we discussed come in handy.
Right. We can use profiling to identify hotspots in our code benchmarks to measure the impact of our changes, and tracing to understand the flow of data.
It's like having a whole toolbox at our disposal.
Exactly. And just like a skilled craftsperson, you need to know which tool to use for the job.
So let's say we've identified a bottleneck in our code. What are some common strategies we can use to address it?
Well, one of the first things I always look at is caching.
Caching. Yeah, we talked about that earlier. It's like having a mini fridge next to your desk so you don't have to go all the way to the kitchen every time you need a snack.
Exactly. And there are many different types of caching, each with its own trade-offs. You might have in-memory caches, disk caches, or even network caches.
So many options.
Yeah.
It's about choosing the right tool for the job.
Exactly. And the key is to understand your workload and your access patterns.
So if I'm dealing with data that's frequently accessed and relatively small, an in-memory cache might be the way to go.
Right. But if you're dealing with larger data sets or data that's not accessed as frequently, a disk cache might be more appropriate.
Makes sense.
Yeah.
And there are also different caching algorithms, right? Some prioritize recency, some prioritize frequency. It can get pretty complicated.
It can, but the good news is that there are a lot of great resources out there to help you choose the right caching strategy.
So caching is one tool in our optimization toolbox. What else do we have?
Another powerful technique is parallelization.
Parallelization. That
Mhm.
sounds like it could really speed things up.
It can. It involves breaking down a large task into smaller subtasks that can be executed concurrently.
So instead of having one worker doing everything sequentially, you have a team of workers tackling different parts of the project at the same time.
Exactly. And with multi-core processors and distributed systems these days, parallelization is more important than ever.
But it's not always the right solution, is it?
Right. Some tasks are just inherently sequential, and trying to parallelize them can actually make things slower.
So it's important to understand the nature of the workload before you start breaking things up into parallel tasks.
Absolutely. And there's also overhead involved in managing and coordinating those parallel tasks, so you have to weigh the benefits against the costs.
Makes sense. So caching, parallelization, those are two big ones. What else?
Another important area to focus on is reducing I/O operations.
I/O operations,
Ugh.
like reading and writing to disk or sending and receiving data over the network.
Exactly. Those operations can be really slow compared to CPU operations.
So it's all about minimizing those trips to the slow parts of the system.
Precisely.
Yeah.
And there are lots of techniques for doing that.
Like, what are some examples?
Well, if you're working with databases, you can optimize your queries to retrieve only the data you need.
So instead of pulling down a whole table, you just grab the specific rows and columns you're interested in.
Exactly. And you can also use techniques like asynchronous I/O to avoid blocking operations.
So your program can continue doing other work while it's waiting for data to be read or written.
Right. And sometimes just reducing the amount of data that needs to be written to disk can make a big difference.
Like compressing the data or using more efficient data structures.
Exactly. It's all about being mindful of those I/O operations and finding ways to minimize their impact.
This is all great stuff, but I'm always a fan of seeing things in action. Does the book provide any real-world examples of these optimization techniques in action?
It does. In fact, there's a really interesting case study about optimizing the performance of a web server.
Oh, web server case study. I bet a lot of our listeners can relate to that.
I'm sure they can. So in this case study, the engineers used a combination of caching parallelization and I/O optimization techniques to dramatically improve the server's performance.
Like, how dramatic are we talking?
We're talking orders of magnitude improvements in throughput and response time.
Wow, that's impressive. What were some of the key things they did?
Well, one of the first things they did was implement a caching layer to store frequently accessed web pages in memory.
So they essentially created a shortcut for those common requests.
Exactly. This reduced the load on the back-end application servers and made the website feel much snappier.
Makes sense. What else?
They also used a technique called load balancing to distribute incoming requests across multiple servers.
So instead of having all the traffic hit one server, it's spread out among several servers.
Right. This ensures that no single server is overwhelmed and that the workload is evenly distributed.
It's like having multiple checkout lanes at the supermarket instead of having everyone queue up at a single register.
Another great analogy. And to further improve performance, they also optimized the way the web server handled static content like images and CSS files.
Ah, static content. That's usually a big part of a website's overall size.
It is. So they used a technique called Content Delivery Network, or CDN, to cache those files on servers located closer to the users.
So if I'm in California and I'm accessing a website that's hosted in Virginia, the static content will be served from a server in California instead.
Exactly. This reduces latency and improves download speeds.
Very clever. So they essentially created a distributed network of caches for their static content.
Precisely. And those are just a few examples of the many optimizations they implemented.
It sounds like they really pulled out all the stops.
They did. And the key takeaway is that there's no single magic bullet for performance optimization.
It's usually a combination of multiple techniques working together.
Right. And it's an iterative process. You make a change, monitor the impact, and adjust accordingly.
So it's not just about knowing the techniques, it's about knowing how to apply them effectively.
Absolutely. And that comes with experience and a lot of experimentation.
Well, this has been a truly enlightening deep dive into the world of systems performance.
I've enjoyed our conversation.
Me too. We've covered a lot of ground today, from the foundational concepts to advanced techniques, and even explored some real-world examples.
And hopefully our listeners are feeling inspired to apply what they've learned to their own systems.
I hope so,
Yeah.
because at the end of the day, performance optimization is all about making things better for users.
Exactly. Whether it's a website, a mobile app, or a complex back-end system, it's all about making those systems faster, smoother, and more enjoyable to use.
And that's something we can all get behind.
Absolutely. So until next time, happy optimizing.
And keep diving deep.